What is partitioning in Spark? Imagine you are standing in front of a mountain of millions that need to be sorted. If you try to do it alone, you'll be there for years. This is exactly what big data looks like to a single computer. That's where we enter into Spark partitioning. Instead of tackling the mountain as one gained pile, Spark breaks the dataset into smaller, manageable chunks called partitions. Think of these like work packages because the data is split up. Spark can hand them off to different executor nodes. Think of these as your team of assistants. Each assistant or CPU core grabs one package and starts working. This is the heart of parallelism, doing 100 things at once instead of one thing 100 times. If you want speed in Spark, partitioning isn't just a feature, it's the fundamental law. This is the core mechanism of distribution. But here is one catch. Simply splitting the data isn't enough. You have to split it fairly. If you notice on the left side of our screen, in a perfect world, every node gets the same amount of work. They'll all finish in 2 seconds. High-five and move on. That's even data distribution. But now look at on the right side. This is every Spark developer's nightmare. This is data skew. Imagine dividing two assistants, one book each, but giving the third assistant 10,000 books. The first two assistants finish instantly and sits around drinking coffee, while the third one, the Straggler, struggles for 20 seconds. In Spark, your entire job is only as fast as your slowest partition. If one node is overwhelmed, your whole cluster is stuck waiting. Balancing your partition is the difference between a job that takes minutes and the one that takes hours. And you may be wondering, how does the Spark decide which record goes where? It uses two main strategies. First, there is a hash partitioning. Spark takes a piece of data like a user ID, runs a math formula on it, and drops it into a one bin. It's like sorting a mail by the last digits of a house number. It's great for spreading things out randomly and evenly. Then the second, range partitioning. This is like sorting mails by zip code. All the mails from A to M names go to one bin and from N to Z go to another bin. This is perfect if you know you'll need to search for a specific range of values later. Finally, sometimes you need to fix your work midstream. If your data is a mess, you'll use repartitioning. It's like dumping all the mails back onto a central table, a process called a shuffle, and dealing it out again perfectly. It's expensive and slow, but it fixes the straggler problem. On the other hand, if you just want to clean up after filter, you use Coalesce. It's much faster because it does not shuffle everything. It just gently merges nearby boxes to save space. Master these strategies and you won't just be running Spark. You'll be orchestrating a high performance data symphony. So the final takeaway of this partitioning in Spark is there is a golden principle. You don't want too many partition, which creates high management overhead, or too few, which leaves CPU cores sitting idle. Aim for 2 to 4 partitions per CPU core in your cluster as a starting point. Balance is everything. Always keep an eye out for a data skew. If your data isn't distributed evenly, the Straggler effect will bottleneck your entire pipeline regardless of how many nodes you add to the cluster. Shuffle wisely. Remember that repartition involves a full network shuffle, which is like a massive traffic jam of your data. Use it strategically to fix skew, but prefer Coalesce when you want to reduce the number of partition after a filter. And finally, know your data. Choosing between hash and range partitioning depends entirely on your query pattern. Use hash for border distribution and range for sorted span based analysis. Ultimately, a well partitioned Spark job minimizes the shuffle, that is the network movement, and maximizes parallelism, that is the simultaneous work. By mastering these two, you transform a Spark from a simple tool into a high performance engine.